Hello everyone, this is Wei-Chung Lai and my teammate Lingling Qu. Our topic is going to be on human protein atlas image classifications. This is a multi-label classification problem. The data set that it provides use it provides gives us like a lot of images that needs us to classify it into appropriate corresponding 28 classes. We need to train a model that will allow us to do so, and hopefully by showing the results and the performance metrics we use, we will be able to show how well our model performed. So basically, this is the contents of our presentation. The first one we're going to be talking about our performance matrix, and this kind of sort of provide a guidance to see how well our model is trained. Then we're going to provide an end-to-end pipeline that shows how we create a model, how we train our model, and how we execute it to provide the results. And lastly, we'll be showing you our first initial performance and some of the issues that we got while training, and also some suggestions that we can make to improve our model to get a better result in the future. So, uh, first of all, is performance metrics. We use F1 score to evaluate the model. F1 score is really common and in the deep learning society because it is a really good index to show how well your model is trained. It is a trade-off between two values. So the recall is the number of true positives over the number of positive samples. And the precision is the number of true positives over the number of positive predicted samples. So based on the equation, 2 times the recall times precision over the summation of recall and precision will be showing you how well our model trained based on this index. And another one is that we are going to be using the loss function. The loss function we're going to be taking on is called binary entropy cross entropy functions. And by the end of the presentation, we'll be showing you 2 graphs. One is the F1 score of the performance of the model, and the other one is the loss of the model while we trained. So we're going to be talking about the end-to-end pipeline. Here are the 4 steps of creating a model. First of all, we use Keras based on TensorFlow as a programming frame, and we read the test and training data from the data sets. Later on, we're going to be constructing a model, a 4-channel CNN deep neural network that help us to do the training. And CNN is really suitable for image classification, which is what composed of our data sets. The typical CNN architecture stacks a few convolutional layers, each one generally followed by a value layer, then the pooling layer, then another few convolutional layer, and a root value. So it sort of repeats, as you can see on the right of this, the right graph of this presentation. It repeats in a set of group. We have batch normalization, convolution 2D, and value, and sort of repeats on itself. Once in a while, we add a max pooling 2D layer and a dropout layer to regularize the sample and the results to get a better result. And then we later on concatenate together and do a pooling and batch normalization again. So the batch size that we initially use is 128, and the epoch that we decided to take on is 100. We use model.fit underscore generator in Keras to train the model. After the model is well trained, we'll be using test data and to test the model and get a test result, and hopefully shows a good result. If not, then we're going to just tweak a little bit of our hyperparameter, which is our batch size and epochs, to get a better result. So here's our initial performance of the F1 score of our training model. As you can see, here are two results that we're showing here. The first one is individual F1 score for each class. Here the model, the result has 28 entries because we corresponding to 28 different classes. And we also have a macro F1 score cross validation. It shows the macro F1 score of cross validating of 0.48%. The second category is the probability of thresholds maximizing the cross-validation F1 score for each class. Again, here there are 28 entries in the results. So here's the initial performance of the result. We sort of graph it as a graph after 100 epoch. The x-axis is the number of epoch, and the y-axis is the performance in accuracies and precision. So basically, as you can see, it's when we start training, it's really low, and it gradually increases the accuracies as we increase the number of epochs, both training and validation sets. And also, when you see the left graph, the training loss and validation sets is skyrocketing in the beginning, and it gradually exponentially decreases to a really low result after we run many epochs. So here's some issues and suggestions. First of all, we're talking about issues. It's kind of hard time to setting up the environment because me and my partner, we both own a Mac. Which is run on CPU. We don't have like a GPU based PC. So we kind of have to set up. We think of sort of different viable options, such as running it on GCP, the Google Cloud Platform, or even AWS. But the environment setups really drives us kind of crazy because we don't really know how to do it, and it takes us a long time to do it. We need to SSH the thing and then make sure that our local host is connected to the VM instance back in the cloud, and we need to also upload our data as well because they don't really have the data online, which takes us a long time. So, but later on, our teammates suggest a different way that we can just basically run our data sets on one of the free platform provided by Kaggle, and it's completely free. It provides a free GPU, so we can really do our training without any importing or any uploading the data sets because it already has the data sets in its database. So that's really saved us a lot of time. And here are some suggestions. So after getting an initial result, we decided to use the different loss functions because we think that maybe binary cross entropy loss is probably not gonna perform that well. So we will be trying to seek for other possibilities such as cross categorical entropy and so on. And lastly, we're going to be, in order to show that our model really trains well, we will probably have to make some adjustments such as changing the batch size, the drop rate, and epoch to try to see under what circumstances does our model gives the best results. So hopefully we'll be improving based on those suggestions that we mentioned. Thank you so much for listening.